Alright, continuing on with our examples of applying infinite limits. In example 3 here, we're supposed to find all the horizontal and vertical asymptotes of y equals 2x squared plus 7x minus 4 over x squared plus x minus 6. So first of all, for the horizontal asymptotes, we need to look at the limit as x goes to infinity of the function. And we need to look at the limit as x goes to negative infinity of the function. And then for the vertical asymptotes, we need to identify the candidates. So we're going to figure out where x squared plus x minus 6 is equal to 0. That factors as x plus 3 times x minus 2. And so our candidates are x equals negative 3 and x equals 2. And so we're going to look at the right and left hand limits for both of those. So we want the limit as x goes to negative 3 from the left, and the limit as x goes to negative 3 from the right, and the limit as x goes to 2 from the left, and the limit as x goes to 2 from the right. Once we've found all those limits, we'll know what all the vertical and horizontal asymptotes are. So I'm going to pull out my calculator, and I'm going to type into my y equals screen my function. So I've got a quantity 2x squared plus 7x minus 4 over quantity x squared plus x minus 6, and set up my table. I'll do these limits in order, so I'm going to go down to ask, find the infinite limits. First, as x approaches infinity, and it looks like that limit is approaching 2. Go ahead and put that down. Do the same thing for negative infinity. And again, it looks like that limit's approaching 2. And so we've got a horizontal asymptote at y equals 2. And then I'll handle the vertical asymptotes. I go into my table set and change it back to auto. And first I want the limits around negative 3. I'm already set up around negative 3, so we'll go ahead and go to my table. And we're getting bigger and bigger negative numbers as we approach from the left, and bigger positive numbers as we approach from the right. So that'll be negative infinity, and that'll be positive infinity. And so we have a vertical asymptote at x equals negative 3. And then I'll go ahead and do the same thing at x equals 2, set up my table. And it looks like we're approaching negative infinity from the left and positive infinity from the right. And so x equals 2 is also a vertical asymptote. Okay, another one. Find all the horizontal and vertical asymptotes of this function. So we need the limit as x approaches infinity of the function, and the limit as x approaches negative infinity of the function. And we need to figure out our candidates to be vertical asymptotes. We set our denominator equal to 0. And if I solve this by factoring, we get that our candidates are x equals 3 and x equals 5. We want to find the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right, and the limit as x approaches 5 from the left, and the limit as x approaches 5 from the right. And this is really all you need to show on these, is the actual finding of the limits and what their values are. There's nothing else that I'm going to expect to see from you in a problem like this other than statements of what these limits are. And as you get better at this, you've probably picked up a few tricks from an algebraic standpoint that you don't necessarily need to go through the whole process of finding these limits, especially for the ones approaching negative infinity and infinity. So set up my table to ask. Looks like we're approaching 3 as we approach positive infinity. Oops, missed a 1. Happens sometimes with my calculator, it's a little finicky. And again, it looks like the limit there is approaching 3. Ooh. And now we will handle the limits at the finite values. So go back to my table set. Change it over to auto. And first I want to find the limits around 3. So I'll go to my table. It looks like they're both approaching negative 5. So we do not have a vertical asymptote at x equals 3. Set the table up now around 5. And from the left, looks like we're approaching negative infinity, and from the right, we're approaching positive infinity. So we do have a vertical asymptote there. So we've got horizontal asymptotes at y equals 3, and vertical asymptotes at only x equals 5. Alright, on to some more examples here. Another way we can apply infinite limits is with end behavior models, and you can read through and explore the ideas in the notes at the top of this page. I'm going to go straight to the examples. We're supposed to find an end behavior model for y equals 6x to the fifth, blah, 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 blah. Okay. Now, in order to find an end behavior model, the easiest way to do it with a rational function is realize that as x goes to infinity, the only part of each of these, the numerator and denominator, that have any sway on the end behavior are the biggest powers of x that appear in those. Because I always explain this as, think about it. I have a gravitational pull, but my gravitational pull is way less than the gravitational pull of the Earth, okay? Which is way less than the gravitational pull of the Sun. And the end behavior models are similar in this case. If you want to look at the end gravitational effect of me, the Earth, and the Sun, the only one that really has a major impact is the Sun. And so that's the same way this behaves here, is only the biggest term really has power on the end behavior model. So I look at the biggest power of x in both the numerator and denominator, and I ignore all the rest. And this is the easiest way to write an end behavior model from a rational function. We ignore all the rest, and we simplify the ratio of those two. And when we do that, this will be a good end behavior model for our original function. And if you compare these two, quantity 6x to the 5th plus 3x squared minus 2x plus 8 over quantity 3x squared plus 7x plus 13 and y equals 2x to the third. I'm going to go ahead and bold the graph of y2 here, make it thicker, and let me set that graph up in a standard window. And if you look at these graphs close to the origin, you don't really see, actually you're starting to see some closeness in the behavior of these two graphs, even close to the origin. But if we zoom out just a little bit, you'll see that these two graphs, as we go out towards infinity, really start to look like one another. And even just zooming out that far, you see the similarity in the two graphs. You saw that the thicker graph kind of just traced over the thinner graph. And so as we go further and further out, these two, their behavior looks more and more similar. And that's why we'll use y equals 2x cubed as an end behavior model. It has the same behavior at infinity as the other function. Okay? Now, let's do that here. Go ahead, you try it, pause the video, and then come back to look at the solution. Okay, so I look at just the biggest powers of x in both the numerator and the denominator. And I'll go ahead and I take that. Write that ratio and reduce. And this ends up being 1 over 2x squared. And that will be a good end behavior model for the original rational function here. Its behavior as x goes to infinity will mimic the behavior of the original function. Okay, that's the end of this lesson, and see you next time.